It was 1935. Einstein was near the height of his fame. He had escaped Nazi Germany in 1933 with the Nazis' good riddance. World War II would not break out for another 4 years, and despite tensions in Europe, scientific inquiry continued to experience the greatest boom it would ever have, with new, earth-shattering discoveries being made annually. In both the pages of academic journals and in live discussions, Albert Einstein found himself at odds with the giants of quantum physics, Niels Bohr and Heisenberg, when he criticized their interpretations of quantum experiments. Meanwhile, another father of quantum physics, Erwin Schrödinger, had, after a conversation with Einstein, published his famous cat thought experiment as a direct attack on both Bohr and Heisenberg's beliefs. The thought experiment, so popular today as an illustration of the counterintuitiveness of quantum theory, caused a lot of shrugging and so what among some physicists, while others found it incredible. Yet it did not answer any questions. Ramping up his attacks, Einstein, with his laser-like insight into the real problem, then collaborated with Podolsky and Rosen to publish a description of one of the most famous experiments in quantum physics. Einstein's criticism, since known as the Einstein-Podolsky-Rosen paradox, or EPR paradox, has confounded physicists trying to understand how to interpret quantum measurements ever since. So, what exactly is the problem? It helps to go back to a foundational demonstration of quantum theory called the double-slit experiment. More than any other, this experiment shows how quantum physics deviates from classical in jarring terms. And rather than look at it with a particular interpretation in mind, consider just what the setup is and what you see and what you would expect to see. The experiment begins with a question: is light made of particles or is it a wave? To figure this out, we need to understand what are the precise differences between particles and waves. After all, we know that water is made of molecules containing 2 hydrogen atoms and 1 oxygen. Although water can have waves, it is made of particles. To understand, therefore, if light is made of particles or waves, we really mean, is there a smallest constituent of light that behaves like a particle in the same way that the smallest constituent of water does? Quantum physics already tells us that light at a given frequency, color, has a smallest constituent. Today we call them photons or light quanta. Isaac Newton called them corpuscles and was adamant that they must exist. They are also called wave packets, and that is part of the problem with thinking about light. It does come in packets, and we know that is true because of the way that bodies, including individual atoms, absorb and emit radiation. In fact, it was precisely this fact that Einstein used to explain the photoelectric effect, which is the basis for solar panels, converting light to electricity, light-emitting diodes, LEDs, converting electricity to light, and lasers, converting light of many colors to light of one color, as well as how we understand light from stars, absorption spectra, and how we identify the atomic constituents of matter with mass spectrometers. Once you establish that fact through many experiments, it seems like you are done. Light is a particle. But then, if light is a particle, it should behave like a particle and not a wave when emitted as individual quanta. That means it should not refract around corners and it should not spread out as a wave front. As with many experiments that have changed the world, this one defies intuition. To understand this, we set up a very simple experiment. It involves a source of light that is capable of producing individual light quanta, a light-absorbing barrier with 2 very narrow slits cut into the center very close to each other. How wide they are and how close together depends on the frequency of the light, but we are looking at fractions of a millimeter. On the other side of the barrier is a detector, like a light-absorbing film, or for something more modern, a set of CCDs as in a digital camera. Let's assume they are CCDs. We put the whole apparatus in a dark box. The results are instantly transmitted to a computer outside the box. When you send light through a double slit like this, the light approaches the barrier as a wave with a straight wave front that is parallel to the barrier. When it impacts the barrier, much of the light gets absorbed, but some will hit the slit openings and pass through. The light that hits the openings, however, will not continue on with a straight wave front as it was before it hit the opening. Rather, some of the light will refract around the corners of the opening and you will see instead a circular wavefront emitting from each slit. If there were only one slit, this circular wavefront would just grow to become mostly straight, what we call a plane wave, and make a big blob of light on our detectors. And when we perform that experiment, With either of the slits covered and only one open, we do indeed see that result. But with two slits open, we see instead that the two circular wavefronts emerging from the two slits interfere with each other. Sometimes, the wavefronts are both rising at the same time and combine to rise twice as much. Sometimes one is rising and one is dropping at the same time, and those combine to give a very weak light or nothing. The result is a pattern of light and dark bars on our computer screen. If light were made of individual particles, however, you would expect that as you drop the amount of light you are emitting to individual light quanta, you would no longer see the pattern of light and dark, because now the particle has nothing else to interfere with as it passes through the slit. It either passes through the right or the left slit and continues on to the screen. As you try the experiment, you might think that is what is happening because each time your laser emits one light quantum, you see one dot appear on the computer screen. It is very clear that one particle is showing up, not a big but weak blob or weak interference pattern that would indicate a wave-like packet. But as you continue to shoot more particles through, a familiar pattern begins to appear. You still see the interference pattern. It looks like the particle is interfering with something, even when there is only one, yet it is making the impact on the screen that a particle would make. Welcome to wave-particle duality. There is no way out of the conclusion here that light has both wave-like and particle-like behavior. The setup of the experiment does not determine whether the light acts like a particle or a wave, as some popular explanations falsely suggest. For example, some misguided explanations suggest that if you put a detector in a place where you can tell which slit the light goes through, it behaves like a particle. But it is not true. The light always has both wave and particle nature, no matter what your experiment is. All your setup does is determines how much information about the light's path from emitter to detector you measure, because that determines what you will see. If you measure the slit the particle travels through, you will not see the particle going through both at once. But the duality is still there since the wave-like nature doesn't cease to exist. It turns out that all matter has the same duality as light. This experiment has been performed with electrons, for example, as well as other particles. This isn't even the weirdest aspect of quantum theory, but I want to stop here because if this is at all new to you or you haven't thought deeply about it before, your head is probably spinning trying to grasp what is going on here. And that was really what Einstein, Bohr, Heisenberg, and a decade later, Richard Feynman, and a decade after that, David Bohm and Hugh Everett, and others were all trying to understand. The light was clearly showing up at one spot on the detector like a particle, and presumably being emitted as one particle from the emitter. So what the heck was going on in between? In the early days, there were essentially two sides to this debate. There were those who believed that the particle was following a definite path with a clearly defined state between emitter and detector. This was the side that Einstein would take, and later David Bohm and John Bell would clarify. This side is called the incomplete interpretation, meaning that quantum theory is incomplete because it can't explain the behavior of that individual particle in between emitter and detector. Sometimes this is also called the hidden variable interpretation because what is happening is hidden. On the other side was Heisenberg, who believed that the act of observation caused the light to appear as a particle at a particular spot, which was called wave function collapse, and that in between it was actually spreading out like a wave. This interpretation, which somehow got attributed to Niels Bohr in later decades, is called the Copenhagen interpretation after Bohr's native city. This is an example of a complete interpretation because it says that quantum theory does explain what is happening, but acts of observations are somehow outside the realm of quantum theory. Bohr's own interpretation, complementarity, was subtly different from Heisenberg's and closer to Einstein's relativity in that he believed that quantum particles did not have definite hidden states as Einstein averred. Rather, Bohr believed that the measured particle and measurement apparatus were both essential parts of the measurement being made. Measurements were dependent on the observer as much as the observed. His interpretation failed to find many followers other than the late great John Wheeler, who said, "Bohr's principle of complementarity is the most revolutionary scientific concept of this century and the heart of his 50-year search for the full significance of the quantum idea." Meanwhile, like the famous cat paradox Heisenberg's strange observer initiated, collapsing wave function interpretation became standard, with Bohr's as a famous name to attach to it. until physicists who didn't know any better started to believe that there was something special about being a conscious entity observing the outcomes of experiments. Of course, that was all nonsense. Both Einstein and Heisenberg got their clarifying heroes in later years. Einstein got David Bohm, who developed Bohmian mechanics, an evolution of an earlier 1920s theory called the pilot wave interpretation. Bohm's goal was to restore classical intuition to a quantum theory he believed had become overly mathematical. If you want an intuitive way to understand the double-slit experiment, Bohmian mechanics is easy enough. It simply introduces a special guiding wave that guides the light particle to the right spot on the screen. Thus, the part we see is the particle aspect of the light. The part we can only see indirectly by where the particle ends up is the guiding wave. It is as if the light particles are little boats floating in a sea of the guiding wave and ending up naturally in a wave pattern because, unlike the particle, which only goes through one slit, the guiding wave goes through both slits at once. Heisenberg, on the other hand, got Richard Feynman and his sum over histories. Feynman's ideas are not exactly synonymous with the Copenhagen interpretation, but they are difficult to reconcile with Bohm's. Feynman's idea was that every point on the screen is the result of the light particle following every possible path from emitter to detector. The probability of the light appearing at any given point was the sum over the probabilities of all paths from the emitter to that point. This naturally leads to the idea that the light particle actually does follow every possible path somehow, and that when we observe it appear at a point, all paths that are not compatible with that observation vanish from existence. Feynman's sum over histories makes intuitive sense from a certain mathematical point of view. If you are familiar with probability and statistics, it will make more sense to you. In Feynman's view, places where the waves interfere with one another are places of low probability. Places where the waves reinforce each other are places of high probability. The benefit is that it removes the wave-like nature from the interpretation entirely in favor of many copies of the particle. Feynman's ideas are an example of a complete interpretation of quantum theory, and there are several ways to interpret them beyond Copenhagen. Many other complete interpretations were developed in the 1950s, including the many worlds interpretation with Feynman's particle paths representing the particle in different universes and the particles interacting between universes until they hit the detector. Any rational person, if given a choice, would probably choose Bohm's interpretation over that. Yet, Bohm found that his interpretation struggled to keep up with developments in quantum field theory, the theory of quantum particles in particle accelerators. His theory did not work with Einstein's theory of relativity for one thing. Even worse, it had no way to deal with particles being created and annihilated. John Bell attempted to fix Bohm's theory by introducing sudden random jumps between different realities where particles existed or did not exist. It was intriguing, but took away some of the benefits that Bohm's original interpretation had given. Ultimately, as quantum theory progressed, the promise of a true particle theory became less and less likely as quantum field theory introduced virtual particles. These are particles that have a measurable effect on the universe but don't actually exist. It seemed as if quantum theory had lost the thread of reality, or if you believe in a complete interpretation, maybe our intuition is simply an illusion. In a Bohmian interpretation, virtual particles are not necessary because the guiding functions take on that role, which again seems intuitive. Yet, if you try to approach quantum theory from Bohm's perspective, you immediately run into a snarl of complex mathematics as you try to solve equations for guiding functions and particles that you actually measure. It is one of the strange realities of modern physics that simple, down-to-earth theories could not compete with the complexity and abstractness of quantum field theory. Bohm managed to replace the confusing, counterintuitive notions of cats being dead and alive at the same time until you look and particles being everywhere until they are in one spot, with a very classical Newtonian sort of dynamics that simply had another invisible player, the guiding function. Indeed, Bohm's program to erase the quantum theory that Heisenberg had built and replace it with an earlier understanding of physics almost seemed successful, but ultimately he failed. Rather than erase it, the great theoretical physicist Mikio Namiki suggested that Bohm's interpretation was just an attempt to develop a new quantum theory with a new way of turning classical physics into quantum. Quantization is the term. Namiki went on to suggest that Bohm's theory, while an interesting interpretation, could not handle complex many-particle systems and fields without falling apart. In other words, it was too fragile for real physics. You can see this in the simple fact that Bohm's theory depends, like Isaac Newton's physics, on the existence of an absolute time. The reason is because the guiding function, when interacting with many particles, must interact with them instantaneously, all at the same time, to explain quantum experiments and the mysterious phenomenon of entanglement. But I will save entanglement for a future video. For now, it seems an intuitive understanding of quantum physics eludes us. Thank you so much for watching. See you again in the next video. Until then, as always, keep looking up, stay curious, and dream big.